main window, and then canvas. I have some things to do here. Okay, and we will want to make some plot data, of course. So this is where the audio processor comes in. We need to create that class. And in that class, we'll be using the same things that we've been using before this. Okay, class audio processor. Okay, so def init self audio file name. And then we'll do seg. We'll do the usual thing, pydub dot audio segment dot from file audio file name. Okay, so we do that, and then self dot samples equals numpy dot array seg dot get array of samples dot reshape, and we do -1 seg dot channels. Let's see, I am wondering, is this console window big enough for people to see? Maybe let me know in the comments if this is too small. I'm trying to figure out how to, maybe Control plus? Okay, let's do that. Ooh, okay, that's probably much better for the viewers here. Okay, so yeah, what we've done, let's see, what have we done in here since... Okay, I'll post a link to the code probably, just in case you miss it. Just in case you missed the first part when I was zoomed out. Okay, so this is the audio processor. So we initialize the samples, and then self dot sample rate equals seg dot frame rate. Alright, self dot end window size, and this is just an arbitrary variable we initialize to 4096 in this case, but we can play around with this window size. Self dot and frames equals int self dot samples dot shape 0 divided by self dot end window size. This will give us how many windows there are. So it'll give us the number of samples divided by the samples per window. That'll give us the count of windows, the number of frames that we process. And then the other thing is the shape of this samples. If it's a stereo, like an MP3 file that has a left and a right channel, then the shape will be, it'll have two elements in it. It'll be, the first one is the sample number, and then the second one will be the channel. So like self.samples, like 15. 0 is the left one, 15.1 is the right one, for instance, where 15 is the... Okay, I'll take that out. Alright, we need to define calc frame. This one will calculate the ith frame. Frame samples equals self.samples. Then we take that. Then we do I times self.end window size, or... Actually, not or, through I plus 1 times self.end window size. That's the usual thing we do. And then 0. This 0 is to select the left channel. Okay, and there's no reason for the left channel specifically, but we need to select some channel or a combination of the channels, and it's easy to just select the first channel in there. Okay, so the T0 or T0 and window size, okay, I times window size divided by self.sample rate, okay. So that'll just give us the start time, which we don't have to use for our transforms. Note list equals numpy dot a range 24, 132, 0.25. This is basically, these are meaty note numbers, and that's the step. Okay, time list equals numpy dot lin space. Okay, so we'll give it, we'll start with T0, why not? From T0 until T0 plus self.end window size divided by self.sample rate, and then self.end window size. So again, linspace, you specify the starting point, and then the first value, and then the last value, which in this case is our first value plus number of samples divided by sample rate. Actually gives us the time in seconds, which makes sense. That's what we're initializing, the time list here. And then the window size, the third parameter to this linspace, tells it how many samples to put. Okay. And then I mentioned in the last video that there is this thing called windowing, and we can do, we'll do just one for now. To do, use a window. Okay, just to see what the difference is. F equals node to freak. Take the node to list dot reshape -1 1. So that'll put all the frequencies on the first axis, and then t equals time list dot reshape 1 -1. This will put all the times on the second axis, and then we can do ph, it stands for phase, -2 times numpy dot pi times f times t. So that gives us the phase. 2 pi ft is your typical physics wave equation, at least the exponent for the, and then the minus is of course to do a downshift, and then numpy dot exp 1j times, you put the I there as well, so that it's complex. It's a complex exponential. SW equals, SW in this case is shifted windowed, even though it's not windowed yet, but frame samples times win times sh dot sum axis equals 1. Okay, so what this will do is it'll take the, and actually this should be frame samples, I believe. Is that what we named it? Yes. Okay, instead of frame sample. Okay, so it'll take the samples, it'll multiply them by the window, and then it'll downshift them using this downshift, and then we sum over that axis. Okay, so then the other thing we need is make some octave ticks, and what these are just node list %12 equals 0. What we're trying to do is we don't want it to randomly, we don't want matplotlib to randomly choose where to put the tick marks on the x-axis, because we know where the octaves start and end. We'd rather prefer it to plot by octave, and so that's why we are telling it to do that. Let's see, t0, we'll just save these values. ts is time list, let's see, ns is node list, lw is the log intensity windowed, numpy dot log 10, numpy dot absolute, sw. Okay, and then octaves, octave ticks, and samples is frame samples. So we return some values. Okay, so this will be our audio processor. That's all we have to do for it. And then here, audio processor equals audio processor, audio file name. And do note that we can name this variable anything, processor2 or something. I named it audio processor just because I didn't have any other names to name it. And then we replace this none with audio, let's see, audio processor. And so this will initialize that, read in the MP3 file, and then it'll pass it to our window object, so that we can also have something to plot. Okay, now this won't quite plot it yet, and let's see if I forgot anything. Yeah, so as I said, this won't quite plot it yet because we didn't actually tell it to plot it yet. We only read in the file.